Hi class, I thought we'd take you through some of the basics of differentiation. I know it's a topic that we've just started. Take you through a couple of examples of how to do the simple differentiation, how that extends then onto first principles, which is a technique we learned just before the shorter method. Now, first principles can be a little bit daunting at first, and it's definitely not something you use all the time. Very rarely you use it, but you still do need to know how to use it. Hopefully, I'll see if I can do a 10-minute video here and explain some of the basics and put some of those pieces together. So we'll start off and look at a basic parabola y equals x squared. Now, why do we differentiate any sort of function? What are we interested in learning? Well, by differentiating this function, we'll get a new equation, and that new equation is what we call the gradient function. We can then substitute any value of x into this new gradient function, and it will tell us the exact value of the gradient of any tangent on any point on the graph. So basically, it's going to tell us how steep this graph is at any location. That's a really powerful technique because not only does it help us work out the gradient or the rate of change at any point on the graph, but we're going to apply it fundamentally for the rest of the course to find the turning points on a curve. Where is the gradient equal to 0? So this point here on the parabola at the origin, we can see if I was to put a tangent line across that point. So a tangent line, remember, is just a straight line that touches the curve at one particular point. That would have a gradient of 0. And in fact, any turning points on any curve, so a vertex on a parabola, for instance, will have the gradient of the tangent will be 0. So if we can work out what the gradient function is and solve when it equals 0, we can find the location of any turning point on any curve without having a picture of the curve, just having the equation. So let's have a look at this. Y equals x squared. The notation for differentiation, getting our first derivative, there's a few different ways you can write it. You can write dy dx. That stands for the first derivative. Another way you could write it, if you wrote the function as f of x like this, you could do the first derivative just by putting a little dash there. A third way, and it's the way I use most commonly when I'm doing work solutions, is to do y with a little dash there. The little dash there means that you're doing the first derivative. So if we get the first derivative of x squared, all we do is we take any equation that has a power like this, take the power, multiply it by the coefficient, so in that case it'll be 2 times 1, so it'll give us 2. The x here will remain unchanged. This power will reduce by 1, so it'll go from a 2 to a 1. And as you know, anytime we have a power of 1, we could write the 1 if we wanted to, but we can generally just leave that blank. So the first derivative of y equals x squared is, and I'll just put the little symbol there so we know it is the first derivative, is 2x. This is the gradient function of the parabola y equals x squared. So again, what can I do with this function? What's the point of this function? Well, I can substitute any value of x into this equation, and it'll tell me what the gradient of this curve is, anywhere on the curve. So if we just do that real quickly, I'll just do a quick table of values here, and we'll go from -2 up to 2, and we'll see what the value of the first derivative is. So if we start with 0, if I substitute 0 into the gradient function, 2 lots of 0 is 0. If I substitute x equals 1 into the gradient function, we would get 2, and if I substitute 2 in, we would get 4. Similarly, if I put in -2 and -1, hopefully you can see quite easily that we would get those values. Now, what do they mean? Well, if we go over to the curve here, the gradient of this curve at x equals 0 is 0, which, there's that line that I drew a little bit earlier. At x equals 1, the gradient, so at this point here, if we were to draw a tangent line on the curve, it's a little bit hard to draw for me, but you can imagine if we had a nice straight line with our ruler, that would have a gradient of 2. And you can see that if I was to slide that up, the gradient of this curve is getting steeper and steeper as we go along. And so if we go up to x equals 2 up here, you can see that tangent line is even steeper than it was at 1, and in fact it has a value of 4. Hopefully then you can see in the negative region here, any all the gradients here will have a negative value. And we can see at -1 it's going to have a value of -2, and at -2 it's going to have a value of -4. It's going to get more negatively steep, if that's the proper term there. By first principles, now this method here, and you're going to do the derivative of x squared, and you're not even going to think about it very shortly. It's just going to be 2x. That takes literally 5 seconds. First principles takes a little bit longer, and you'll very rarely do this unless you're specifically asked, but we just covered it in class, so here's how you would do it. First thing we're going to do is rewrite this using that function notation. Anytime you do first principles, we need basically two elements here. We need this element, take away this element, well, we've already got that, all over h. And then at the end, we're going to substitute h equals 0 into the equation, and that should give us the gradient function. I.e., spoiler alert, for this one here, we're going to get y dash, or function dash, equals 2x. That's going to be our final answer. And if you've done this shorter method now, it's always a good idea to just differentiate using this shorter method to know what you should end up with at the end. So first thing, let's have a look at what is the function of x plus h. So anywhere in this function, wherever you've got an x, we're going to substitute x plus h in place of x. We'll do the expansion. So if you did that expansion, try it yourself. You should get that expression. Pause the video there and then try that yourself if you haven't done that yet before. So now we've got these two expressions. If we substitute them into a fraction, we're going to get this expression. Take away, so I've just substituted this part in. Now we're going to subtract the original function, which was x squared. Anytime you use first principles, you're always in the top here. Once you do this process, you're going to cancel out the original function, and everything else is going to stay there. So x squared is going to cancel out, and we're going to be left with these two terms at the top. Now all I'm going to do is put h at the bottom, and we have this fraction. Fractions, we've got h squared and 2hx here, so we're going to cancel out the h's, and we're going to be left with, after we tidy that up a little bit, 2x plus h. Our last little part there was to do this limit. The limit is h equals 0. Basically, we're going to substitute h equals 0. And if we do that, we're going to be left with our final answer, which we knew before we even started this bit, that the first derivative of the gradient function of x squared is equal to 2x. Let's have a look at another example. We've got a linear function y equals 2x minus 1. So we've got a linear function this time, a straight line, and a linear function, as we know, has a constant gradient. So what would we expect if we got the first derivative? Well, the first derivative for this particular function, y dash, I've got a power of 1 here, so 1 times 2, that would give us 2, x to the power 0. Anytime you have a 2x or 4x, 5x, whatever the case may be, to the power of 1, pretty much this disappears and we're just left with the coefficient. Also, when you differentiate any constant terms, plus, minus, doesn't really matter, any constant terms become 0. So the first derivative of a linear function, 2x minus 1, is simply, in this case, is equal to 2. What does that mean? Well, have a think to yourself. Y equals 2x minus 1. If we thought of that in terms of y equals mx plus b or mx plus c, what is the gradient of this line? The gradient of that line is the coefficient of x in the equation, and in this case is 2. The first derivative is the gradient function. It tells us the value of the gradient on the line, anywhere on the line. Sometimes, like a parabola, that was a variable equation, i.e. it varies for different values of x. But for a linear function, have a look, the derivative function has no x there, it's just a number, which means that the gradient of this particular function is constant. It has a value of 2 the whole way along the function. I hope that kind of makes sense. the reason why all constant terms, when we differentiate them, become 0, if we think about this, if I had a function y equals 2, have a think real quick, y equals 2, what would that look like on the graph? That would be a horizontal line. I'll just draw it as a dashed line here. A horizontal line that goes through y equals 2. What would be the gradient of that line? The gradient of that line is 0 because it's a flat horizontal line. So that's why the first derivative of any constant term like that becomes 0. In this case here, it just disappears. First principles, if we do our first principles here, we've got this here is our function of x plus h. We substitute x plus h in anywhere in here where there's an x, so that will become 2x plus h minus 1. Expand the brackets, 2x plus 2h minus 1. And then if we do the first derivative, if we substitute that function in that we just did, minus the original function. So here's the original function. I'll put that in brackets. And that'll be all over h. Have a look if what cancels. So we're going to get 2x minus 2x, so that's going to cancel. We're going to have minus 1 plus 1, so the 1's will cancel. And all we'll have left here is 2h over h. The h's will cancel. And by first principles, that linear function, the gradient function, is equal to 2. Again, you might ask yourself, well, what's the point of this if we can just do it in 2 seconds like this over here? Well, you're shown this when you first learn calculus to show where it comes from, because basically this is being a gradient function. This is really just an extension, if you had a look at those first notes from that first day, of the gradient equals y2 minus y1. There's y2, there's y1, all over x2 minus x1. Go back and have a look at those videos on the first derivative and the gradient function if that doesn't quite make sense. But for some functions, it's a little bit trickier to do this shorter method. Like any trig function, exponential functions, this can be a useful method. Last example, we've got a concave down parabola. I'm going to quickly go through and show you now. As I said before, one of the most common uses for differentiation is to find these what's called stationary points, turning points. In this case, it's the vertex of this parabola. We've learned a few methods to do that already in the course, but if we differentiate, we're trying, at any of these turning points, the gradient of a tangent at that point would be equal to 0. It'll be a horizontal line. So to find the location, if we were to differentiate this function, so the 2 will come down the front here, we'll get minus 2x to the 1, and we can just leave the 1 off there. This term here, plus 6x, will just become plus 6, and the minus 5 there will disappear. And our gradient function of this curve is minus 2x plus 6. I want to find where does this gradient equal 0? Where is the turning point? Well, we could solve this equation here. It's a two-step equation that you learn in year 8. Take the 6 over that side, divide by 2, and lo and behold, we could see that on the graph anyway. The gradient of the tangent is going to be 0 at x equals 3. Very powerful stuff. Which obviously we've got the graph here and we can see that, but for complicated curves, anything, if we just have the equation, we can work out those turning points without even having to draw a graph. And in year 12, you're going to use this technique to actually sketch curves, to use the equation to find where the turning points are, and then that'll allow you to sketch, especially cubic curves, where there's going to be at least maybe 1 or 2 turning points. Very quickly to finish this video off, if we did first principles, a little bit more complicated with more expressions here, but if we were to just do the f of x plus h, so f of x plus h squared plus 6 lots of x plus h minus 5, let me just change the pen there. If we expand that term out, we're going to get minus x squared plus 2xh plus h squared plus 6x plus 6h minus 5. Now, if we just have a think about this, that we've got that term there, the original term, whenever we do first principles, that original term will cancel out with any term we have here. So here's the original 3 terms. So in this expression, the x squared is going to cancel out, the 6x is going to cancel out, and the minus 5 is going to cancel out. So we're going to, if we do this derivative function, we're going to be left with this term here, so minus 2xh minus h squared, and we're going to have this plus 6h here at the end. That's going to be all over h. If we cancel the h's out now, we've got h will cancel with that, this h will cancel with the squared, and the h will cancel here, and we're going to be left with minus 2x, so this term will come along. We're going to have the plus 6, and we're going to have the minus h. Our last part of this is to substitute h equals 0 if we have any h's left over, and in this case we do. So this bit will cancel out, and we will get the gradient function, which, yes, we got over here in a matter of 2 seconds. My advice to you guys is to make sure exercise 6.04, that shorter method, go over that, make sure you go through every question so that you can do, at the very least, this shorter method, and try at least 3 or 4 of the first principles, so that you start, especially doing the first principles of a quadratic, so that you can see going from this expression to this expression, very common. Hopefully this video helped you. Ask me send me an email with any questions if when you do 6.04 you get any difficulties. Okay, have fun.